What's up guys, it's me, Sir Ernest, and today we're going to talk about position and displacement in Cartesian coordinate system. So this is the first two fundamental quantities or physical quantities that we're going to discuss as we start our study of Newtonian mechanics and mechanics in general for single particles. So let's say if we have your usual Cartesian coordinate system, x, y, and z. Now, if the particle is found somewhere here, and let's call this point P, with coordinates x, y, and z. Now, the position vector r is given by this vector, and it is usually written with r with the vector sign. So if we're going to get or set the projections of the position vector in the x, y, and z coordinate system, we can draw it like this. So this one will be your z component. So if this is a vector, we could also put in the unit vector k hat here. If you're going to set this point to be projected in the xy plane here, so therefore the x component and the y component are written as follows. So this is your y j hat and I hat. Here we already set that this is your unit vector I hat, this is your unit vector k hat, and this is your unit vector j hat. Now, the position vector r is now given by the x component I hat plus the y component j hat plus the z component times k hat. So this is your position vector, especially if we're going to set this, if we're going to represent the position vector in unit vector notation, we write this as such. So here we assume that the x, the position vector r has three components, x, y, and z. Now what happens if this, let's say the particle move to another position? Okay, so let's say this is the position of the particle at time equal to t. So let's call this position 1. Now let's say this particle move, let's say following this path. Okay, and it ends up in this position. Let's call this P2, given by a new set of x, y, and z. So in this case, we can now define the position vector at this point. So let's call this r at time plus at time t plus some in time interval dt. Okay, so here we now have two positions, r at time equal to t and at r at time equal to delta t. So from here we can actually say that the particle move in this direction, and from here we can define the vector that expresses the change in position. The change in position is given by this vector. Let's call this dr. Okay, so here we define the following. We define the time interval, delta t, which is equal to the time at time equal to 2 or 0.2 minus time at time equal to at a position point P1, or in terms of the interval, we can actually say this is dt, if this dt or delta t is very small, so this will be equal to t2 minus t1. So the initial position is given now by rt, and the final position is given by rt plus dt or delta t. So from here we can define our displacement vector delta r vector, which is equal to r t plus dt minus r t. Okay, so if this is your displacement vector, so that means we can actually define the final position, okay, as given the initial position r and your displacement vector delta r. So this is now your final position r at time equal to t plus dt. Okay, so as you will notice that this expression actually is consistent to the definition of the resultant vector, wherein if this would be your r at time equal to t, and let's say this will be your delta r, so that means the resultant of these two vector will be your final position r plus dt. Okay, so that's it. That's your simple description of how we represent position and displacement of particles in Cartesian coordinate system, especially using the unit vector notation. Okay, so in the next video we're going to talk about how the displacement changes with time. So that means we're going to talk about velocity and acceleration. So in the meantime, thank you very much for watching. I hope you learned something today, and I'll see you guys in the next video. Bye bye.